Okay, let's begin talking about polynomials. And let's start off with an example. An oil pipeline bursts in the Gulf of Mexico, causing an oil slick in a roughly circular shape. The oil slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. If we wanted to write a formula for the area covered by the oil slick, we could do so by composing two functions together. The first is a formula for the radius r of the spill, which depends on the number of weeks w that have passed. So we need to find a formula for the radius of this spill. So the radius, we can call this formula r of w because the radius depends on the number of weeks that have passed. This is equal to, let's see, this says that the slick is currently 24 miles in radius. So it starts out at 24 miles in radius, and it increases by 8 miles each week. So this formula should be r of w is equal to 24 plus 8 times w. Now if I want a formula for the area of this circle, well, the area of a circle is just pi r squared. And I have a formula for r. So if I want to find the area of this circle as a function of week, then I would have to compose a of r and r of w to find a of r of w. This is going to be the same thing as a of 24 plus 8w, which is going to be pi times 24 plus 8w squared. And if I multiply this out, see, this is pi times 24 plus 8w times 24 plus 8w. This is pi times 24 times 24 plus 8w plus 8w times 24 plus 8w. I'm using the distributive property here. This is pi times, let's see, 24 times 24 is 576. 24 times 8, that's 160, plus 32, that's 192. So 24 times 8w is 192w. 8w times 24 is once again 192w. 8w times 8w is 64w squared. Now if I combine my like terms here, again I still have a pi on the outside here, so I'm going to distribute that in here in a second. 192 plus 192, because I have w's with both of those. This is 384w. And now I can distribute a pi to everything. So a of w is 576 pi plus 384 pi w plus 64 pi w squared. This formula is an example of a polynomial. A polynomial is the sum of terms each consisting of a vertically stretched or compressed power function with non-negative whole number power. We stress non-negative instead of saying positive, because this means that this power could be 0 also. So let's get some polynomial terms. Here's a little box that has some terminology of polynomial functions. A polynomial is a function that can be written as f of x equals a naught, or a sub 0, plus a sub 1 x plus a sub 2 x squared plus dot 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 plus a sub n x to the nth power. Each of these a sub I constants are called coefficients. So these a's are just numbers, is what it's saying. These are stand-ins for these coefficients. And these coefficients can be positive, negative, or 0. And the coefficients can also be whole numbers, decimals, or fractions. So these coefficients can be any real number. A term of the polynomial is any one piece of the sum. That is any a sub I to the times x to the ith power. So for instance, this a2 x squared is a term of that polynomial. Each individual term is a transformed power function. We say that the degree of the polynomial is the highest power of the variable that occurs in the polynomial. The highest power that you see is the degree of the polynomial. The leading term is the term that contains that highest power. It's the term with the highest degree. And the leading coefficient is the coefficient of the leading term. So it's the number that the variable with the highest power is being multiplied by. Because of the definition of the leading term, we often rearrange polynomials so that the powers are descending, so that I have the highest power first, followed by the second highest power, etc. Not every polynomial that you see will be given to you like that, but that's how we prefer to order them if possible. So let's look at some examples. Let's identify the degree, leading term, and leading coefficient of each of these polynomials, starting with A. Let's see, for f of x here, the highest power that I see, so I have a power of 0 with this first term, with this 3, right? Because that's 3 times x to the 0th. I have a power of 2 with this second term, because x is being raised to the second power. And I have a power of 3 with this third term, because x is being raised to the third power there. So for this function, the degree is 3, because 3 is the highest power of x that I see here. The leading term, remember, is the term that contains this highest power. In this case, that would be negative 4x cubed. And the leading coefficient is the coefficient of that term, the number that the variable raised to the power is being multiplied by. So my leading coefficient in A is negative 4. For B, the highest power that I see here, let's see, I have a power of 5 in this first term, I have a power of 3 in this second term, and I have a power of 1 in this third term. So the highest power I see is 5. So the degree of polynomial b here is 5. The leading term is the term that contains that degree, or that power. So this means that my leading term is 5t to the 5th, and the leading coefficient is the coefficient of that term. This means that my leading coefficient here is 5. And for C, let's see, if I'm trying to find the degree of that polynomial, this first term has a power of 1, because that's like p to the first power. The second term has a power of 3, because p is being raised to the third power. This last term has a power of 0, because 2 is the same thing as 2 times x to the 0th. So in this case, my degree is 3. The term that contains that power, that is my leading term, is negative p cubed. So my leading coefficient, the coefficient of this term, is negative 1. And let's talk about long-run behavior of polynomials. For any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. So let's look at an example. What can we determine about the long-run behavior and the degree of the equation for the polynomial graphed here? Well, since my output is growing large and positive as my inputs grow large and positive, we can say that as x approaches positive infinity, f of x is approaching positive infinity. And similarly, as I go to the far left, as my inputs grow large in the negative direction, my outputs are also growing large in the negative direction. So I can say that as x approaches negative infinity, f of x is approaching negative infinity. So I've talked about the long-run behavior. As far as the degree goes, I can say that this has the shape of an odd degree power function. Because this has the shape of an odd degree power function, that means that the degree of the polynomial creating this graph has to be odd. And this graph did not undergo, well, it has the same shape as the graph of an odd degree power function that has not been reflected. So this means that my leading coefficient is positive. And let's talk about short run behavior. So because polynomials are functions, they will only have one vertical intercept. This will be at the point 0, a naught. However, they could have multiple horizontal intercepts. The horizontal intercepts occur at input values that correspond with output values of 0. So horizontal intercepts are also called zeros or roots. So there can be multiple horizontal intercepts. Let's say, given the polynomial f of x equals x minus 2 times x plus 1 times x minus 4, let's find the vertical and horizontal asymptotes. Not asymptotes, I mean intercepts. My bad. I don't think that we haven't talked about asymptotes yet, but we will, I believe, in this chapter. So my vertical intercept occurs when my input value is 0. So this is just as simple as finding f of 0, which is 0 minus 2 times 0 plus 1 times 0 minus 4. This gives me negative 2 times 1 times negative 4, which is 8. So this graph crosses the vertical axis at the point 0, 8. For my horizontal intercepts, or my x-intercepts, this occurs when output is 0. So in other words, when 0 equals x minus 2 times x plus 1 times x minus 4. So notice that this expression on the right-hand side is equal to 0 when any of these three pieces in parentheses is equal to 0. So I can take each of these and set them equal to 0 individually and solve for x. I get x equals 2, x equals -1, and x equals 4. So this means that my horizontal intercepts are the points 2, 0, -1, 0, and 4, 0. So let's look back up at this example here. Notice that in this example, that this particular polynomial has 3 horizontal intercepts, and it has 2 what we'll call turning points. It has 2 places where the graph changes direction, right? The graph changes direction about here at this black dot, and back down here at this black dot as well. So we're going to make just a general statement about intercepts and turning points. We won't justify it yet, but perhaps we will later. A polynomial of degree n will have at most n horizontal intercepts an odd degree polynomial will always have at least one. And a polynomial of degree n will have at most n minus 1 turning points. So now, let's look at our last example. What can we conclude about the graph of the polynomial shown here? This is a rather vague question, but maybe first we'll talk about long-run behavior. Well, because as my x's grow large in the positive direction, my outputs are also growing large in the positive direction. And as my inputs grow large in the negative direction, my outputs are growing large in the positive direction. This has the graph of an even degree polynomial. This graph has 2 horizontal intercepts, one here and one over here. This means that it has degree of 2 or more. And this graph has 3 turning points. The 3 turning points means that this has degree of 4 or more. So I can erase this previous line, right? 4 is greater than 2. So the 3 turning points suggest that this has degree of 4 or more because a polynomial has at most n minus 1 turning points. If n minus 1 is equal to 3, then n is 4 at least, right? Now we did use the phrase at most, so it's possible that this is actually greater than degree 4. But we can definitely say that this polynomial has an even degree. The degree is at least 4. So it might be reasonable to conclude that this is a 4th degree polynomial. And this will be it for section 3.1.